Dear students, continuing with our lecture series on bioorganic chemistry, this is our 31st lecture in the series, and today we will know the chemistry of enzyme immobilization. As you know, that enzymes they act as biocatalysts, but have some drawbacks in terms of their cost effectiveness for various technological applications. So there is always a trend that enzymes they should be used in an economical way. So different methodologies are developed to utilize these enzymes, which are very costly otherwise, in an economical manner. So for that purpose, in recent years, enzymes they have been confined to specific solid sports, which may be polymers, synthetic polymers, or natural polymers. And when these enzymes they are physically attached or chemically attached to these solid sports, they become confined and they can be used successively and repeatedly for their biocatalytic activities. So, such enzymes uh, which are physically attached to a specific solid sport and thus their movement is confined, and these can be used repeatedly and continuously while maintaining their catalytic activity. They are called as immobilized enzymes. So they have a few advantages, like a single batch of enzyme can be used multiply or repetitively in an process as a catalyst. Then it has also been found that in most of the cases, the immobilized enzymes they do not lose their catalytic activity, and they have been found to be more stable than the mobile enzymes. Mobile enzymes, the enzymes which have not been confined to any sport. Then the reaction with these immobilized enzymes that can be controlled rapidly by removing the enzyme from the reaction solution, because the enzyme is now confined to a solid sport. If we remove that solid sport from the reaction mixture, the reaction will stop. So in that way we can control the reaction by removing the enzymes from the reaction solution. Then the enzymes which are immobilized, they can be easily separated out from the product, and there will be no contamination in the product formation. Then this will also allow the development of multi-enzyme reaction system. For example, if we require more than two enzymes in a reaction, or two enzymes or more than two enzymes in a reaction system, then these can be used simultaneously or even in a single step. So the technology for development of multi-enzyme reaction system, that can also improve with the use of immobilized enzymes. Then immobilization of these enzymes can be done by different methods. The main two types of immobilization is reversible immobilization and irreversible immobilization. Reversible immobilization is that once you immobilize the enzyme, then by the reverse process it can be generated back. The enzyme in its native form can be generated back. That kind of immobilization is called as reversible immobilization. Whereas irreversible immobilization is that once you have immobilized the enzyme, you cannot recover the native enzyme from that process. So that is called as irreversible. immobilization. Now, the example of reversible immobilization is adsorption. So, when the enzyme will be adsorbed on a solid surface physically, then by desorption process it can be recovered back also. So that is why adsorption is an example of reversible immobilization. Whereas the covalent bonding of the enzyme to the sport will lead to irreversible immobilization, because then once the chemical bonds have been formed with the enzyme system and the sport through some linkers, then we cannot recover back the native enzyme. So covalent bonding, entrapment, encapsulation, and cross-linking, all these types of immobilization reactions, they come under the category of irreversible immobilization. But the reversible immobilization has some advantages over irreversible immobilization. First thing is, in case of reversible immobilization, there will be no chemical modification of the enzyme. Because there is no chemical modification of the enzymes, that means the activity of the enzyme cannot be retarded by this process, because active sites, they will remain active because there is no change chemically in the structure of the enzyme. And if the enzyme gets activated during the use, then it can be replaced in reversible immobilization. Then third is that immobilization of enzyme by adsorption of bioaffinity, that can be done very fastly. So this process is a faster process than the irreversible modification. Now we can depict these different types of enzyme immobilization. That is, if this is a sport which may be a synthetic one or a natural one, when the enzyme is physically absorbed on the surface of this sport, then such type of immobilization is called as adsorption immobilization. And this can be reversed also by desorption process. The enzyme can be removed from the spore, because this is only a physical phenomena, and there are no chemical bonds which have been formed between the sport and the enzyme. Then covalent bonding is that when the functional group present on the sport forms a covalent bond with the functional group present on the enzyme. So here the structure of the sport as well as that of enzyme is modified by forming a chemical bond. So this type of immobilization is an irreversible process, because the structure of both enzyme and the sport has been changed. Then this entrapment or encapsulation, this is when some polymers they surround these enzymes, and then such type of immobilization is called as encapsulation or entrapment. So difference being, in encapsulation we are having a semi-permeable membrane, so it will allow certain particular substances to enter these encapsulation medium, and they can interact with the enzyme molecule. And then another category of immobilization is cross-linking. Cross-linking is when different enzymes or protein molecules, they are cross-linked through some linkers, which may be chemical compounds, to form bonds in a three-dimensional structure. Then this type of linkage is called as cross-linking immobilization. Now, first, the reversible immobilization, that is a phenomenon of adsorption. So immobilization by adsorption, this is the easiest and the fastest method by which we can immobilize the enzymes. And this type of immobilization depends on many factors like pH of the system, nature of the solvent which is being used for adsorption, then what is the ionic strength of the medium in which the adsorption is taking place, then what is the quantity of the enzyme and the adsorbent on which this enzyme will get adsorbed, then how much time we give to the process. This will also determine that what is the quantitative nature of the adsorption in that particular process. Then temperature also matters in case of adsorption, because this is a physical phenomenon. As I've told you, advantages of reversible immobilization or adsorption method is that the methodology is easiest and fastest, and here we don't require any additional reagent except the adsorbent, that is the medium on which the enzyme is to be adsorbed. Then almost no activation of the sport or the adsorbent is required for these types of adsorption methodologies, and this is comparatively economical method in comparison to other irreversible immobilization techniques. Then here, because this is a physical phenomenon, the active sites of the enzyme, they remain active, and there is almost no inactivation of the enzyme take place during adsorption, which is seen by other chemical methods like covalent immobilization or cross-linking immobilization or encapsulation. So, in comparison to irreversible immobilization, we find that this adsorption immobilization shows less inactivation of the enzymes. So basically, the process is done in this way that what we do is we soak the sport uh, on which the adsorption, sport means adsorbent, on which the adsorption is to take place into a solution of the enzyme for some time, say a few hours, and then this enzyme will get physically adsorbed on the adsorbent, and the process of adsorption is due to the weak forces which are non-specific, and depending upon the type of adsorbent and the enzyme, we will have either hydrogen bonding or van der Waals forces or hydrophobic interaction among the sport and the enzyme for the adsorption to take place. And these relatively weak non-specific forces, because they are weak in nature, so this reaction can be reversible also, that the adsorbed enzyme can give back the native enzyme and the adsorbent back. And this can be done if we change any of these variables like pH, ionic strength, temperature, or purity of the solvent. So, by changing these, we can either absorb the enzyme on the spot, or we can desorb the immobilized enzyme into native enzyme. The next is covalent bonding. As I have told you that covalent bonding is the formation of a covalent bond between the sport and the enzyme functional group. So the stable complexes they are formed when the function group on enzyme molecule and function group on support matrix they form a covalent bond. So such type of immobilization is called as covalent immobilization. So the functional group which are present on the enzyme and are used for covalent bonding, they should be other than the functional group which are responsible for the enzymatic activity. So the functional group which are used, they are non-essential for enzymatic activity. Otherwise, if the functional group for enzyme activity is used for covalent bond formation with the support, then the enzyme will become deactivated. So we need to concentrate on this aspect, that only non-essential functional groups they should be used for formation of a covalent bond between the support and the enzyme. And most commonly the essential groups for enzymatic activity, for example in case of lysine it is amino group which is responsible for the catalytic activity of the enzyme. In case of cysteine it is thiol group, sh group, which is responsible for the enzymatic activity of the enzyme. Then in aspartic and glutamic acid active sites, it is the carboxylic acid group which is responsible for the enzymatic activity of the enzyme. So that means in case of lysine or cysteine or aspartic acid, these groups they should not be used for forming a covalent bond between enzyme and the spore, because these are catalytic groups which are responsible for the activity of the enzyme. So the mainly the enzyme functional group which are used for covalent coupling, they are amino group, carboxylic acid group, phenolic group, sulfhydryl group, thiol group, imidazole group, indole group, and hydroxyl group. But these groups which are being used, they should be non-essential for enzymatic. So some of the examples of formation of a covalent bond for covalent immobilization. So the process can be divided into two parts. First is that the sport with which the enzyme is to make a covalent bond, that should be activated. And this activation of the sport takes place with some linker molecules, and most commonly used linker molecule is glutaraldehyde, and in some cases carbodiamide is also used for this linkage purposes, and some other anhydride groups they are also used in some cases. Then after the activation of the sport, then covalent coupling of the enzyme take place with the activated sport through linker molecules to give us an covalently immobilized enzyme. So for example, if say we are having this sport, and on this sport we are having these amino functional groups, and when we add glutaraldehyde to this sport, what will happen? Because this is having an aldehydic functional group, this carbonyl will react with this amino group, and removal of water will take place, and a carbon nitrogen double bond will be formed. So this will lead to the activation of the sport. So sport activation take place on reaction with the linker molecule, and a carbon nitrogen double bonded compound is formed with the sport. Then this activated sport will then react with the enzyme molecule. Say our enzyme will bind to this sport through amino group again. Then enzyme immobilization will take place. Again, this amino group will interact with the keto group of this aldehyde, and removal of water will lead to the formation of this type of immobilized enzyme. And the active sites of the enzymes are present in this protein part of the molecule, and rest of the molecule is not going to interfere with the enzymatic activity of this enzyme or protein. Similarly, another example, if we are having this type of uh, sport, say polyacrylonitrile, for example, in which we are having cyano groups present on the surface of the polymer. So these cyano groups, they can undergo activation in presence of sodium hydroxide. So hydrolysis of this cyano group will take place, and some of the cyano groups, they will be hydrolyzed to give us carboxylic acid on basic hydrolysis, followed by action with first sodium salt of this carboxylic acid will be formed, and then on reaction with HCl neutralization we will form these types of activated sports. And these activated sports, then through this carboxylic acid, they will react with the non-essential active sites of the enzymes, and this amino group will interact with the carboxylic acid group to form an imide linkage, and we will get these types of immobilized enzyme where the sport is attached to the enzyme through this covalent bond. So that is why this is an example of covalent immobilization. Then another example of covalent bonding, this type of copolymer of maleic anhydride and this styrene molecule. So polystyrene maleic anhydride copolymer on reaction with enzyme. So this amino group will interact with the anhydride part of this molecule, and we will get these types of immobilized enzymes where you can see there is a formation of a covalent bond between this port and this enzyme. Similarly, nanofibers, these types of nanofibers which are having epoxide rings present on the nanofiber, they can react with enzyme molecule to form the covalent attachment of enzyme into these nanofibers, and this is again an immobilized enzyme where the covalent attachment of the enzyme has taken place with the sport. Now, as far as advantages of covalent bonding is concerned, that covalent immobilization, the linkage of the enzyme to the sport is very strong. So, when this linkage is very strong, that means the leaching of the enzyme into the reaction solution will be minimum, or there will be no leakage or desorption of the enzyme during the reaction. So the comparatively the enzyme activity will be high because there is no leakage or desorption of the enzyme. And the methodology for covalent bonding is very simple because we are to use only linker which can attach the sport to the enzyme through the covalent bonding. And there are many sports which are available, and sport may be a synthetic sport or it may be natural polymer also, which can act as sports, because natural polymers, they are also having different function groups like hydroxyl group or amino group or carboxylic acid group present on their surface. So these functional groups, they can act as activated spores to react with the enzyme to have covalent bonds. Then, because a vast variety of sports are available, so applicability of this covalent bonding is also wide. So disadvantage is merely that sometimes the conformation of the enzyme changes due to covalent bonding, and because of this chemical modification of the enzyme, the conformation is lost, and thereby, in some cases, because of that, enzyme inactivation has also been observed at the active site. Then entrapment and encapsulation. Here, the enzyme is not directly attached by chemical means to the support surface, but the enzyme is entrapped within a polymeric network like this. Here, the whole molecule, here the individual enzymes, they are entrapped within the polymeric network, and this will allow only transfers of substrate and the product, but enzyme will be retained back in that polymeric network through diffusion. The process is the enzyme is mixed with the monomer solution uh, of the monomer solution from which the polymer is formed, and then that monomer solution will undergo polymerization by a chemical reaction or by changing some experimental condition. So here the advantage is that here also the enzyme is physically confined within the polybernetics, and there is no chemical change in the conformation of the enzyme. Advantages, it will improve stability of the enzyme. Then, because they are confined in the polymeric matrix, that means the leaching will be minimum and denaturation will also be minimum. And capability to optimize microenvironment for the enzyme will take place, and in capsulated material will have optimal pH, polarity, and amphilicity. So these conditions, they will not change because within that capsule the conditions will remain same. Limitation is mass transfer resistance, because of the thickness of the gel matrix will increase as the polymerization takes place. Then entrapped enzymes, they may leak if the pore size of the sport matrix is too large. Then the enzyme loading capacity of these encapsulated materials is low, and because of low enzyme loading capacity, larger reactions, they cannot take place. Reactions where we want to synthesize say products in kilograms and more capacity, then it will be a problem through this process. Then sport material that could be corrupted during the polymerization. So these are some of the limitations of these methods. Then last is cross-linking. So enzyme immobilization by cross-linking, as I've told you, is an irreversible process. And here, what happens is this can take place through two methodologies. One is cross-linking enzyme aggregate, and other is cross-linking enzyme crystal. So these two types of products with cross-linking immobilization can take place. So in the first process, cross-linking enzyme aggregates is that In the first step, the enzyme they undergo aggregation to give us enzyme aggregates, and then these enzyme aggregates through some linkers like glutaraldehyde they undergo cross linking, which is three-dimensional in nature, and such type of enzyme immobilization is called as cross linking enzyme aggregate. Then the other process is cross-linking enzyme crystallization or enzyme crystal. So here the individual protein molecules they will first undergo crystallization, and we will have different definite geometry of the protein molecules, and then these definite geometry molecules or proteins they will undergo cross linking through cross linkers like glutaraldehyde, and we will have these types of materials or immobilized enzymes which are called as cross linking enzyme crystals. So these are the two different processes through which the cross linking can take place. And CLEC method, that is crystal method, as I have told you that glutaraldehyde is added to cross-link the enzyme crystals after crystallization. So they will lead to a significant improvement in mechanical properties of the enzymes. So, because of the improvement in mechanical properties, these CLECs they are usually more stable and having higher efficiency than the uh, non-immobilized enzymes. Whereas these aggregates they are an improved version of the crystalline products they are formed, because these CLEs they can work in aqueous solutions only, whereas these require the formation of crystals. The advantages of cross-linking is that here also the enzyme leakage is minimum, and the possibility to adjust microenvironment for the enzyme by suitable stabilizing agents through surface complementarity will increase the stability of the enzyme. So this is an added advantage that the stability of the enzyme will increase due to cross-link. Thank you very much.